Hello everyone, my name is Alex Kingsbury. I'm with Enlight. Today we're very excited to have this talk today about software. Software is a really important part of the ecosystem for additive manufacturing. And for us as laser suppliers, we need to work really closely with software providers. They're a very important part of making additive manufacturing work. So I'm very excited to introduce today Steve Walton, who is the head of product development for Dyndrite, and also Martin McMahon, who is an industry consultant and a technical advisor with Metal Additive Manufacturing magazine. Over to you guys. Thank you.
Thank you, Alex. So, long time ago in the not so IT-intensive days of manufacturing, people would spend hours, days, maybe even years getting trained up and getting skilled and expert at what they know and what they do. And these days, we have software to do that for us. So I thought I'd ask Steve just to briefly explain what it is that Dyndrite does with their software in a very sort of layman's terms, if possible.
All right. Thank you, Martin. Well, my favorite part about the show actually so far was a conversation we had already this morning where Martin says, I get it now. Dyndrite has been, within metal additive and polymer additive for several years now. We've often gotten this question of how we fit into the ecosystem because we actually touch a lot of different aspects of the workflow. And so what we provide is a set of tools, not necessarily a solution, but the tools for customers to implement their own solutions. Those tools can support process development, process qualification, and also deployment in a production environment. So those tools actually are provided via a Python API. That Python API provides a model of a machine, of parts, and of the process for users to actually help execute that workflow from the development to the production side. So what we have are tools that allow geometric analysis of components and querying the geometry, querying the machine, and in a framework that allows the user to fit within a qualification structure, such as provided by the NASA guidelines. Did I answer that?
Yeah. So one of the things I've struggled with, I was kind of traditional metallurgist engineer, don't really get software, never really learnt how to program anything other than things in BBC Basic when that was the most advanced language of its time. And I think people get confused with things like what's a colonel. Colonel's a regiment in or a rank in the army, as far as I'm concerned. And they talk in language which we don't really understand. But last night, as Steve sent some slides over, and I just had that epiphany moment. So yeah, this actually does click. It does fall into place, and it was quite interesting. So I was just thinking from the point of view of what you're actually offering in laser powder bed fusion, what is it that the software can sort of like make life easier for a user these days?
Okay. So we'll talk a bit about the organizational structure that we have and some of the problems that we're trying to address. So if we start by looking at this part here, we know that we would like to apply different parameters within the volume of a part, right? We would obviously not want to use big high productivity parameters over here when we're trying to make a structure that's fine like this. However, today we have these very bespoke workflows that are kind of set up around the existing machine, the existing software, as opposed to trying to rationally assign and distribute parameters within a part. And so what we actually are doing here is we're providing, I'm actually going to stand up so I can see this a little bit. I'm sorry, Martin.
That's okay.
But we have tools that provide this framework that I mentioned a second ago. So what are we trying to do? Distribute those parameters in the thick sections and the thin sections or the lattice sections. And here are some methods that we provide to do that. We're familiar with upskin, downskin, and shell type operations. We also can do those same operations on a subset of the geometry. And so what we set up, our ability to query these geometries. Once we query those geometries, we can assign parameters. We really start with specimens. We all see specimens all over, tensile specimens, feature specimens, and that's what we use to develop the process because it's easy to characterize. It's easy to set up test geometry. We section things. We look at the melt pool. but ultimately we want to put those in a final part. And so the strategy is start with specimens, define your rules, then qualify those rules in the context of like qualification, sensitivity analysis to your process, but then use the exact same set of queries in the final part. And so the structure that we provide allows you to start really far at the left end of process development, but using the exact same rationale or logic, you can implement it in a part. So that provides a traceability through the entire process. And so that is just where in the part we want to assign parameters. A big problem we have today also, as the machines have gotten larger and added more lasers, is when do we want to do these various operations?
And so machines like the NXG, which you can see over there with Nikon SLM, they have 12 lasers. Order of operations is a big problem on those machines. So we also provide tools for sorting and optimizing the trajectory to minimize laser interactions, minimize spatter, and ultimately make that sort of decision for a 12 laser machine, and then convert that strategy also to maybe a 4 laser machine of a different configuration. So there's both the 3D segmentation tools for where do we want parameters, and then we have to convert that into how do those interact with the machine from an order of operations perspective. So different sets of APIs that you would use in different points of the workflow, but we're really trying to enable new process capability, and that's not something that we claim to be the experts in. We want the user to develop their expertise and deploy it. And that is where the IP is developed and owned by them.
So I was trying to think of how I could put this into layman's terms, make it simple for anybody who isn't really technical to get this. And I came up with an analogy. It's a bit like buying a car for the first time. Anybody can learn to drive a car. I've learned to drive a car, and I guess most of you have done. But if I was to try and race that car around a track and race someone like Lewis Hamilton, then he's going to beat me every single time because he's an absolute expert. And along comes Dyndrite with this wonderful software now that can control my car and make it go faster, and all I need to do is sit back and maybe press the ignition button and let it do everything for me, and maybe steer a little bit every now and then. I think that's kind of like the analogy I can get, is that this software is helping the ordinary driver become like an F1 driver. I think that's a fair comment.
Yeah, I think that's I like the analogy. How do we fit into that? So we provide maybe the chassis and part of the framework for the control system, and maybe the process experts would be the ones developing the traction control system or the ABS system, right? That they then provide to their team, who may be the designers or the applications engineers, to implement on a daily basis. So we help provide that framework for control. Their process experts implement the actual control algorithm for the rest of the organization to use on a recurring daily basis to still be high performance drivers, but not having to figure out how to tune the system from the beginning.
So you, as a company, you spent years obviously developing your technology, and you've been doing it with all of these other wonderful laser systems. And then along comes new kids on the block with this wonderful new laser system that gives you funny patterns and different modes. How do you cope with these different sort of changes in technology?
Well, we'll get through something like this. Really, what we provide again is this framework. We are trying to enable lots of different strategies. We know that we are not the experts in a machine, in a new process, a new laser, and we want to provide again that platform. So an example would be the concept of parameters that exist on an SLM machine, right? We have something like laser focus, power, speed, as an example. Something new like beam shaping comes in. For us, that is something that the user can actually extend our format on their own without talking to us, and incorporate that into their own system. So that's not something we even need to be involved in. And so what we also can do then is some of the machine OEMs, they have their internal formats. They might not necessarily address all of the index mode, for example, or the beam shape mode. However, the open machines, like with Econity, we actually have the ability to add user-defined parameters directly into their format. And so with the, especially the R&D platforms that are designed to be open from the beginning, we don't need to be involved at all. And so again, it's the tool. I'm excited to see the developments and the opportunities. That's not our thing. It's the tool to enable other people to do that. So I hope that, we're not in the, actually. Every time someone comes up and says, we're going to do this and use it in a new way that we never thought about, that's when I get the most excited, honestly.
So you've obviously developed mathematical models, multi-physics models based on standard Gaussian distributions. Along comes these weird donut things. How does that change that model? Is it really difficult to develop these things? I mean, I must admit, I'm not a mathematician or a physicist, so I can just imagine lots of really strange, crazy equations. How do you get that into software?
Yes. So in our case, we're going to jump forward probably a couple slides here. You can see in these parts, we have these different colors shown in the parts. Each of these colors actually can represent a different parameter being applied within the volume of the part. But since we provide a Python API that defines the toolpath, that Python API, you would be able to assign a laser, power, speed, ring mode in each of these different colors. Because if I go back to the API concept, it can be extended with any process parameter definition that you could generate with a Python tool. So in the example before, there are many. It's a very hot area in today where we're looking at modeling the different sort of laser material interactions. A model of this melt pool might be developed by a researcher, and that's something that we would be able to incorporate via Python into parameter definition. So it's as simple as integrating it with a Python library.
So effectively, you're sucking in other people's work into your toolkit.
Our intent is not, as I said, not to be the experts in many of the areas, but to provide the platform for other experts to quickly realize and commercialize their research.
So one thing that really excited me, though, the slides you showed me yesterday, was this aspect of being able to change or use the different beam profiles, and it kind of led to an explanation of what has become quite popular, these supportless builds. And you have distributed, I think you call it distributed spatial distribution, that was the word, sorry. And the idea of being able to pick a parameter or a mode of scanning that then allowed you to build things that had different overhang angles and fill in the gaps with different scan strategies and so on and so forth. And this is something that I've been praying for to come along in the laser powder bed sort of application for absolute years. And it was just like a real magical moment to see that it had actually been achieved in this software. So perhaps you could explain a little bit more about that?
Yes, exactly. Thank you. So the same strategy, right, to apply different parameters within the volume of a part. We evaluate the part geometry. We can look at the surface normals. We have this concept of the part called regions. So we have the entire surface of the part. We can analyze that surface to find local overhang angles or surface normals. So when we detect those, we make different sub areas. You can see like the blue, the red, the yellow, orange surfaces. Those have attributes such as overhang angle. We can then query that local surface feature and determine the melt pool shape that we would like to put in that part. And so an example here is now segmenting this part up into several different volumes. You can see on each of these, we have a yellowish color closest to the surface. And that yellowish color is something that we're going to dynamically change the parameters within. And all the other offset colors will actually grade power through the part. So we don't want to overheat near the surface of the part, but we also want to dynamically change at the closest surface. So this is us. These are our tools for segmenting the part up for parameter assignment. Then choosing the actual melt pool shape that we might want to apply, as Martin was saying, is what we're showing in the top right. This is again this was a PhD thesis from several years ago. Using our tools, we implemented this in a day, more as a proof of concept of how the tools can be used and extended by the user. So a naive application kind of downskin parameters is actually in the middle, when you can see this green, when you see the melt pool shape protruding through the bottom surface of the part. On the right, maybe specific overhang angles, we actually want to apply different melt pool shapes. And so we would be able to analyze that geometry, like I mentioned, find the overhang angle. We also can determine the laser angle of incidence or deflection angle. That might be a further modification that you want to make. And once you determine the shape that you want, you use the model of melt pool shape that could come from one of the multi-physics models, and then choose where to apply the mark and then what parameters to use on that mark. And that is how you achieve that improved surface finish on the far right.
And I guess a lot of this is kind of stuff that you could have done with ordinary lasers anyway. It's standard Gaussian distribution. People have been trying to do it with things like the contour scans and big hatch scans and so on and so forth. What kind of extra benefit do you think you're going to get from the AFX laser?
First of all, the problem has become harder because there's now more degrees of freedom. That's great, right? However, we can now actually tailor larger melt pools, shallower melt pools, and have more design flexibility. So we can achieve this sort of strategy while maintaining productivity, because we can make larger, more stable, faster parameters, as well as some of these what might be slower parameters that we might use near the surface to maintain feature resolution and surface finish. The other aspect of it is through this sort of beam shaping, we do see more stability. So we can have higher certainty that we can implement a strategy like this, as opposed to with a straight Gaussian beam.
And how much work is it, though, so you've developed some scan strategies and some parameters, and all based on, again, standard lasers in some of these systems, and they'll give you known materials properties. So how much extra work is it then to find exactly the same materials properties, but using different laser technology?
That process, I would actually imagine, is almost the same as with the standard processes. However, as we mentioned, it's just another degree of freedom. All right. So, as I mentioned, the Python APIs, they can be used to do this sort of assignment within the part geometry. And really, that's through that sort of automation is the only way you could achieve a strategy like that. But to develop a strategy, we really also want to be able to parametrically explore the design space. There are more degrees of freedom that we're considering. And so via the Python, we can generate automatically these sorts of build layouts to do that space exploration. One of the things that Dyndrite also provides is the ability to change parameters along the length of vectors. And so you could set up those test coupons, test configurations that are used to either anchor the models through generally destructive testing to iterate more quickly. And so the parameter definition can come from the material model. The results can be put back into a database. And really, it's designing the test configuration, in most cases, around the test methods and equipment that an institution may have, right? So you see lots of different coupons optimized for different test methods. We can parametrically define the geometry and the parameter distribution within that geometry to increase that cycle time.
So when you say parametrically define, I'm going to get me if I get this a bit wrong. You're just describing the shape in software of the part, and that allows you then to assign parameters to different parts of that shape whilst you're building the shape, and they can all be different.
That's correct.
So almost like an infinite number of parameters could be used to build a single part. And if you're collecting data then that you want to associate maybe for quality control, that seems to be like an awful lot of data. Is there anything that your tools help with collating that data and reporting it?
Yeah, absolutely. So the registration of the parameters within the volume is something that is done through the definition, but all of the final output files that we have for the toolpath, right? We have many different machine OEMs that we work with, but we also integrate with many of the open formats and also have our own internal format, of course. And that is very simple to query to find where in a volume certain parameters may exist. And so that registration activity with the overlays that I could show in a second enables maybe better, at least alignment with the destructive processes. So that at least helps with that setup. There's no question that it is still a lot of data that needs to be generated and evaluated.
And could that be mapped to, say, non-destructive testing, like CT scanning, that gives you the coordinates of a defect?
Yeah, absolutely. So you see in a lot of the tools for defect studies and parameter robustness tests, you see a lot of people designing defects in CAD and doing those parameter sweeps, often kind of trying to trick the software that they may have.
Yeah.
We can do those sorts of studies explicitly by varying the toolpath via Python, via our toolpath APIs. So things like intentionally omitting hatches or intentionally changing the power parameters maybe to the bounds of what the process control might allow are things that we don't have to trick the software to do. It's very simple to explicitly do those things.
And how do you go about validating that? Are there standards that you have to work to validate all of this kind of information in testing?
That's a great question. So I don't know of any.
Okay.
One of the reasons that we have this software is to address toolpath challenges and deficiencies that are present in many platforms. The cycle time to make improvements to toolpath is generally very long. Each machine has a different toolpath that's generally developed by the OEM around that machine configuration. And so transferring parameters from one machine to another is often difficult or not possible. And certain part configurations may not work well in a certain machine configuration. So our tools are designed from the ground up to enable transferability from one machine configuration to a next, and also allow the user to optimize that toolpath for the part in a machine. So it is not there. I'm not aware of any standards. However, we have a lot of tools to query the actual validity of an output file. Like a lot of hatch vector statistics could be generated. There are actually several companies that are looking into that in the industry right now as kind of higher level surrogate analysis to determine what is good. And we are happy to work with them and provide our file format, the output of that for that sort of analysis, because without that analysis, it really can't be improved.
And in order to sort of really run the software, you say you have to configure the machine in the software as well. So the environment, I'm guessing you have to tell it which way the gas is flowing and which the scan axes are and stuff like that. Are you working directly with the individual machine vendors to do that? But is an individual able to do that and say, well, I've got a machine that isn't in your portfolio. How do I input my machine data?
Yeah, another great question. That is something that we can work with the OEMs, and we do sometimes work with the OEMs to define and understand, characterize the machines. Ultimately, it is those are controls that the end user would be able to implement on their own. So, for example, gas flow, we often want to write hatches upstream in a build file. So where we start furthest downstream, we hatch toward the gas inlet. That might be in a different orientation in a different machine. That's as simple and conceptually as changing the sort direction for the exposure. And that would be a vector, a point you could sort toward. You could sort along a vector, for example. You could calculate the angle of incidence or deflection angles of different lasers. Those lasers are just points in space for us. So whatever mathematical model that you would like to implement as constraints into a sorting optimization routine, that's something that we provide tools for the user to implement in Python. And so you could actually develop a strategy that would work on a machine with 4 lasers in one configuration, and if properly designed, that exact same algorithm could be used on a machine with a slightly different laser configuration.
Right. So another thing that occurred to me when I was looking for the presentation, a lot of it seems to be stuff that you think, oh, that's actually quite obvious that I'm going to need that in the future. Why is it that machine vendors themselves haven't provided these capabilities?
Another good question. In many cases, they offer good solutions. Those solutions are sufficient for the majority of applications. However, as you see, a lot of the large parts, a lot of the large aerospace parts in particular, are designed around the machine configuration, designed around the build volume. They use the entire limits of the machine. We know that often gas flow is constrained near those corners, near the edges, and maybe there are some build deficiencies that could be accommodated by very specific strategies. Mm-hmm. However, each part is different and would probably want a slightly different optimization. That's not something that the machine OEMs really would be set up. They would have to have a new algorithm being developed for each machine and part combination. That's not something that they're really set up to scale to. And that is specifically why we're trying to help address that.
Right. Yeah. Right. And does the set of models or the tools that you've developed, is there any difficulties for one material over another? So that stainless steels might be more complicated to work with than, say, titanium or anything like that?
Yeah, no. The geometric tools that we're talking about really would be material agnostic.
Okay.
Yeah.
So the models of like melt depths and things like that, that's not taking into account alloy complexities.
So as far as those, the model that we showed here was actually just an example model from a PhD thesis.
Right. Okay.
Right. So it's again just a proof of concept of how that could be implemented with our tools. I mentioned that that's really only a day or two of work. Obviously, we know the APIs well. Might take a new user a little bit longer to do that. Right. But if they have their own melt pool model, something like either the results, you could generate a lookup table from tools like Flow3D or ThermalCalc. Those are at least high fidelity tools that could be used to generate a model to be used for any material, really.
So looking ahead, my last question really is that looking ahead as to where 3D printing or additive manufacturing is going, and using the technology of things like the AFX laser, what things do you think have yet to be discovered, yet to be played with, that could be really quite exciting to move us on into levels of higher productivity, greater acceptance by industry, and so on and so forth? Anything you think, I'm burning to give this a go because it's this is something we know that we should be able to do?
Well, I'm very excited to see finally materials developed for the process. We actually have a materials consortium with Dyndrite to help advance these sorts of materials. Yeah. This is a great opportunity. We've started with alloys that were developed for casting, for forging, for other very, very niche applications, but designed around the process at the time. We now have a totally new process with much higher cooling rates, with cooling rates that can be defined by the tool, by the laser that's being used. The opportunity to tailor microstructure within components we can do with the laser and our software. So I think that's a great opportunity. We're just starting to see that, and that's what I'm most excited about, which is why we have that consortium right there.
Yeah, no, in fact, I agree. I think that's having new beam technologies is something that I find really, really exciting. Being able to scan in different ways and tailor microstructures for geometries or even materials properties, I think, is something that we desperately need to do more research on. Right. Well, thank you. Brilliant answers. Any questions from the audience, I guess?
Thank you. I have indeed few questions. The first one, let's assume we have a new part of the equation at the start, as example, a new material or a new beam shape. How do you start? At least you have some standard geometries maybe, and you have then to test for each of these geometries which kind of physical parameter we will apply. So do we have like a standard procedure or standard geometry you're testing physically at the start?
I can say how I would go about doing that and how our tools might be used through that workflow. We don't have a specific geometry. Most users that we have worked with have their own preferred geometry that they would like to use. What we would be able to do is help parameterize a design study. So via Python, you could integrate with your design of experiments tools. You may want to actually parametrically generate the geometry as well. So this example actually up here, that geometry was generated with a free online CAD generation tool that happens to have a Python API. So we're actually using Python to both integrate with a model to generate the parameters and just a solid modeling API to generate the part geometry. But what I would most likely do is start with a high fidelity model, like Flow3D, for example. Anchor that model using actual destructive testing, using a parameter sweep, something like this. Maybe generate a lookup table to then have those overhang fingers, right, that we had before to identify the overhang angles and do that study and use that as kind of the iteration and anchoring loop. So it'd be using the Dyndrite tools and libraries to integrate with several other tools that have, Python APIs in this case. And really you're trying to go through from the highest fidelity model to something that you can then deploy in practice while generating toolpath. So you're going to go from the high fidelity one all the way down to low level surrogate models that can be run quickly for toolpath generation.
But then this is something done by the end user or customer. So he's defining the concrete parameters. So you're providing the tool, and he's making his trials and defining, okay, here this ring mode, here this power, and so on. Okay. I have another question. Do you have like a channel in the communication to external process monitoring where you can read data from whatever system it is, and then even thinking further, maybe then even optimize the settings via machine learning, as example, based on this data you're getting from there?
Yes. So we actually, during the slicing process, when we're generating the toolpath, you can actually intercept the toolpath, the 2D geometry, and also continue querying the 3D geometry model. That information can be used to update the toolpath. So you can intercept that geometry, send it to external processing libraries, and then act on any input that you might have to update the toolpath. An example would be taking like IR camera feedback, using that as like a mask to modify the toolpath that it intersects in some way. So we definitely have libraries to do that. An example, like we showed the power, speed parameters. Maybe you want to decrease power locally in an area. That would essentially be done by overlaying some cutting geometry on the toolpath. And every time like the vectors pass through that, you could change the parameters. So definitely.
I have quite a similar question, actually. Made me think about benchmarking. In the early days, many years ago, there was quite a lot of debate over which was the best benchmark sample part, especially when doing things like parameter development on a new material. So do you see any future of the Dyndrite software using AI, for instance, to try and analyze these benchmark geometries and say, okay, based on how we do parameter development, all this analysis points to this being the best benchmark, and then trying to make that the industry standard? Because I think that's desperately missing from the whole of the AM sector, really, is a benchmark which we all agree on that's the best one that we can do for all materials.
we'd be happy to participate in that discussion. I agree with you that is something that the industry would benefit from. I do think that certainly depending on the methods that you're using, there will be different geometry or different samples that are more appropriate, maybe more expensive to examine. We do work closely with ASTM to kind of at least help with the standards and move, like working on the common material data model. We're also helping them develop standards for build layout and automation of build layouts. That's more on the machine process interaction side for those standards. But there, like you said, there have been several standards proposed so far. It would be very easy for us to implement any of them within these tools. If you want to champion that, we'll get involved.
Is there any AI actually in the software?
No, there's not. So again, this is the Python. Come get some demos here. Anyone wants to come see it in a little bit. But it's a Python API, and with the UI on top of that, that is something that the end user could do themselves fairly easily.
Excellent.
We actually have examples of people doing that.
Okay. Thank you.
Are there any other questions? Okay, can I take the last one? So as a company that designs and makes lasers, we take a lot of our feedback and input from the OEMs that are here, at the show today. And they're the integrators. We talk a lot with them about our specifications, right, and our performance. Is there anything from a software point of view that you would like to see in our lasers in terms of performance specifically?
Yes, definitely. So one of the opportunities that we see is this image on the bottom right here. So if you see some of the parts that we have over on our booth right now, you can see some strategies that actually provide low overhang, unsupported overhangs. That sort of strategy is something that can take extra time and slow the process down. And a way that we have to address that process duration and also reduce the number of jumps in the build process from the laser, from the tool jumping around, is to actually change the parameters along the length of a vector or as you're traversing around the part in the contour. Those dynamic parameter changes we can do with the power and speed with the lasers today. Changing the mode is something that we would also like to be able to do, to be able to change the melt pool shape as we're going around the perimeter of the part. So to be able to do that as fast as the laser is scanning, that means we would like to switch that at the clock speed of the controller, so in the 100 kilohertz type range. So I think that's a great opportunity for future development, so we can take advantage of this sort of strategy to the fullest. Yes.
Fantastic. Happy to say we can do 100 kilohertz, so no problems there. All right. Well, if we're all done, I think we'll wrap up. Thank you so much for that fantastic talk. Really appreciate it. Thanks, guys.